Welcome back to our course on fluorescent spectroscopy, principles and applications. This is going to be part 8A. It's a continuation of our discussion of fluorescence quenching. And today we're going to focus on fluorescence quenching with proteins and with membranes. Last time we spoke about the static and dynamic quenching constants and what their meanings are. Today we're going to talk about the fractions of quenchable and non-quenchable fluorophores and proteins, spectral separation, quenching in membranes and locations of fluorophores in membranes, and some long lifetime fluorophores. There's also going to be a part 8C. I tried to combine these together, but there were too many additional topics to mention, and the lecture would have been too long. So I decided to break it up into part 8B and part 8C, which we'll present a little later. So let's start looking at quenching of proteins, considering we're using water-soluble quenchers, and what we might expect to happen with a protein if it has a single tryptophan residue which is buried within the protein structure, or a tryptophan residue which is on the surface. And of course we would expect something different to happen. There's a very easy example. The later ones will be more difficult, but the easy one to present is the one for apoazurin. There are multiple azurins. The one that's most used is the one with one tryptophan residue, which is the one shown here. But the data that we have is for an azurin that has two tryptophan residues. And what was decided to do is what would happen if we just threw in a lot of potassium iodide, which would quench the tryptophans, and could we get spectral resolution of those two tryptophan residues? And naturally it worked, or I wouldn't have been mentioning it. But anyway, this is the emission spectrum of the wild type protein with two tryptophan residues. And this is the spectrum of the wild type protein, two tryptophan residues containing a lot of potassium iodide to quench the surface residue. And this is the different spectrum. So here we were really able to completely separate the emission of the two tryptophan residues just by a lot of quenching. This was a fortuitous case because normally you're not going to get such an extreme difference between the availability to quenchers, and so it's not going to look as crisp as this. And also apoazurin has the unique feature of having some structure and its very buried emission, a very buried tryptophan residue, which makes the resolution seem even a little more simple. Now, the much more common result is that we have two tryptophan residues, and they're both accessible to quenching, but to different extents. And when this happens, what I should have had here is a picture with two tryptophan residues, but let's just imagine we had a mixture of these two, or we had a protein with both of these residues. When you did your normal Stern-Balmer plot, what you would find out is that it's no longer linear. Instead, it's going to be curved. And it's going to be curved because at low concentrations, you're going to be quenching the more accessible tryptophan residue, and at the higher concentrations, you'll be quenching the less accessible residue. There's an equation that can be used to deal with this. Instead of the Stern-Balmer equation, it's an equation that is formulated so that it can reveal the fractional accessibility to quencher. Now, that might not be the same as the amounts of the two different tryptophanes, because they could have two different quantum yields. But anyway, we do have a graphical way to turn this more complex looking Stern-Volmer plot into a linear plot. So this is the derivation of the equation. I was going to try to explain it and could hardly explain it to myself. So I'll just jump to the conclusion. In order to resolve the accessible fraction of fluorescence from each of these residues, we no longer plot F naught over F as we do in Stern-Volmer, but we plot F naught over delta F, which is a change in the fluorescence. And we plot that versus, not versus the quencher concentration, but the inverse of the quencher concentration. And that changed these complex looking Stern-Volmer plots, because there are multiple accessibilities to multiple residues, into linear plots. So if we make this transformation and we do the extrapolation, what it actually turns out to be extrapolation to very high quencher concentration, we can get the reciprocal, the fractional accessibility, or we could say that half of the tryptophanes are accessible to quenching. I have to admit that the resolution of this method is not very good if the two accessibilities are similar. I was going to try and remove this central green line where the accessibilities are more similar, but they have to be quite distinct in order to resolve them in this type of plot. Well, let's take just one example, endonuclease 3, which is a glycosylase that works for DNA repair. It has two tryptophan residues. If I can find them, there's one here at 132, and another one at 178. And we're going to once again do an iodide quenching experiment on this protein. We'll use this equation that we just described. And first, we'll look at the normal Stern-Volmer plot, and we see that it curves downward, showing there's an initially more quenchable tryptophan and then a less quenchable tryptophan. And if we plot it instead with this other equation, which accounts for the accessible fraction, we get a straight line, and it extrapolates excuse me, to 1/2, which means half of these, one of these residues is accessible to quenching, and the other one is not as accessible to quenching. Let's ask a more complicated question. Can we use the quenching to resolve the individual tryptophan residues in a protein? This is what we did in the first slide with apoagilan, which, because of the very large difference between the accessibilities, you could immediately see that one was quenchable and one was not. The answer to this question as to whether we can do it is partially true, partially false. So if we have some protein that has all these different tryptophans in it in different locations, can we quench it and reach some type of conclusion of what the tryptophan distribution is within the protein? In simple cases with two tryptophan resolution, two tryptophans in it, this can actually work. this is the E. coli TET receptor, which is responsible for resistance to tetracycline. This receptor is bound to a DNA fragment here. We have two tryptophan residues. Just looking at them, they don't seem to have a very different exposure. But if we do look at the quenching curves at different wavelengths, we get very different results. We see much higher quenching at the longer wavelength than we do at the shorter wavelength, which means there's the longer wavelength residue is more exposed to the iodide quencher. The less exposed residue is less exposed to the iodide quencher. Here you really have to perform many experiments at many different wavelengths, different emission wavelengths, and you have to rely on a least squares procedure. So what you obtain is a set of quenching curves which contain the fractional intensities at each wavelength. And you use a least squared analysis to recover the fractional intensities at each wavelength. If you multiply it by the total emission spectra, you can get the emission spectrum of each of the two residues. And this was done for the TET repressor, and it worked like a charm. If you looked at the quenching constant versus wavelength, as we suspected from the first plot, the quenching constant is lower at the short wavelengths and higher at the long wavelengths. If we go through our least squared analysis and try to recover the two emission spectra, we can say here they are. This is the emission spectrum of the wild type of the TET repressor, and these are the two recovered emission spectra for those two tryptophan residues. So I don't know which experiment was done first, but this was pretty much proven to be correct by a more biochemically challenging approach, which was to make single tryptophan mutants of the TET repressor. And if we made the single, that's what we have here, the single tryptophan mutants on this side, for this buried tryptophan, we see that it has, this is the wild type, this is the mutant protein that only has the buried tryptophan, has a small amount of quenching. The mutant protein with the exposed tryptophan has a lot of quenching, and the wild type protein is in between. So the quenching resolution worked for this particular case. I had another example of this for the two tryptophan residues in apomyelobia, which were also resolved by quenching. As you noticed, I wrote an optional slide down here. I didn't think it was necessary to go through all the details, except to say this procedure can work with different proteins. And once again, about half of the residue, half of the intensity was accessible to quenching. I doubt strongly that this would work if there were 3 tryptophan residues in a protein. So now let's move on to something that's more complex, which is quenching in membranes. So let's look at some of the data that we already know for quenching with membranes. We know that membranes undergo a phase transition from a solid form to a semi-liquid form, from a state where the side chains are ordered to where they're disordered. And actually we had done this experiment, and we looked at the quenching of a fluorophore 2-methylandrosine in these 2 different bilayers, which at the temperature of the experiment were either above the phase transition or below the phase transition of the membrane. And basically we found that the bimolecular quenching constant knowing the lifetime of 2-methylanthracene, was about 20 to 40% of the diffusion controlled rate. So that's not much of a barrier to oxygen transport. But another thing to consider is that oxygen is more soluble in non-polar solvents. So the actual oxygen concentration in the bilayers is probably several-fold higher. So that this would have been an underestimate of the overall permeability of the membrane. So we would conclude that the model membranes, there's really no significant effect of the phase state on oxygen diffusion, and in fact there's no significant effect of the membrane at all on oxygen diffusion, just goes right through it. So this is true for homogeneous lipid bilayers. This experiment was also done with erythrocyte membranes, or the ghost membranes, to be more precise, the ones for which the hemoglobin's been removed. And this is a much more complicated membrane system where there's a bunch of membrane-bound proteins. We use this probe. Let's see, it's going to be pyrene dodecyl amino acid. It has a lifetime of about 120 nanoseconds that allows you to calculate the bimolecular quenching constant. And the answer is that the erythrocyte membranes provide only a very small barrier to the transport of oxygen. So even with a lot of proteins in them, oxygen moves freely. And this should have been obvious because the red blood cells carry the oxygen around the body and deliver it to cells. You can get very different results with very, very different lifetimes. So I have two plots here that in a way they look similar, but they're different. Here we have the quenching, once again a tryptophan, but it doesn't matter. And we noticed that we did this experiment with 100 atmospheres pressure of pure oxygen. So it took a lot of dissolved oxygen to get this amount of quenching, even 5-fold. In contrast, if we take this probe, which is a ruthenium derivative, and we look at the amount of quenching, it has about a 5 microsecond lifetime. It was placed in silicone, which is known to have a high solubility for oxygen. And under these conditions, there is 500-fold less oxygen partial pressure than there is in this experiment, and yet we get much, much more quenching. And this is one of the points I've tried to make repeatedly, is that the amount of quenching you get for a fluorophore depends on its lifetime, because that determines the amount of time allowed for diffusion and contact with oxygen before it emits its photon, which I've put on this plot. And the value, I don't know if I'll do a lecture later on long lifetime fluorophores, but the value of long lifetime fluorophores is that they provide high sensitivity when it's needed for something to diffuse, like oxygen or nitric oxide or maybe even a small protein. A longer lifetime gives you more time to diffuse and interact with the fluorophore, and that allows also for very simple instrumentation, a nanosecond or so pulsed LED would be more than adequate. So this could be used as an oxygen sensor. It's sensitive enough that it could follow just a normal breathing. So if you have this this probe in the breathing line. You can see the patient when he's holding his breath, and when he exhales, the amount of intensity goes up because there's more CO2 replacing the oxygen, and then as he breathes normally, you can follow the breathing pattern. Another thing you can do is to image the oxygen concentrations in cells. I was encouraged to do this experiment, although I don't think this was my experiment. But I never expected there would ever be a oxygen concentration gradient in cells. And as you can see here, there is some differences in the probe concentration at different locations of the cells. But the FLIM image, which is the lifetime image, which is really the oxygen concentration image, is homogeneous across the cell. And I think I explained this in adequate detail. But once again, the importance of lifetime measurements and sensing, which we'll discuss in a future lecture on sensing, is that it is very insensitive to intensity variations. So here we were, in fact, running our hand between the light source and the sample and making the intensity go all over the place. We were using the frequency domain method here and measuring the phase angle, and it just stayed dead flat. So that bodes very well for the use of lifetimes in sensing. Location of fluorophores and membranes. This is a much more difficult problem than the problem of just oxygen transport through a membrane. Because when we look at a normal membrane, it's extremely heterogeneous. There are proteins, some proteins are clustered, different lipids in different places. So there's never going to be a single answer to where a fluorophore is located in a natural membrane. There might be a little bit of an answer in a homogeneous lipid bilayer, less likely in a real membrane. But nonetheless, attempts were made to do this. One of the earliest attempts to localize fluorophores in membranes was done using cobalt, which also is a nice quencher of fluorescence. It might be an energy transfer acceptor as well as a heavy atom quencher. And this membrane, which turned out to be, once again, an erythrocyte ghost, was labeled with different NBD derivatives. The NBD chromophore is shown here, and the NBD could have been placed on a cholesterol molecule, and it was placed on different locations along the chain. A longer alkyl chain should be deeper in the bilayer, and it was placed at the phospholipid head group. And we color-coded the results here to make them a little more understandable. So first, let's look at the NBD that was located at the phospholipid head group. Naturally, it's the most accessible to the water-soluble quencher. The two probes that had 6 or 12 carbon atoms between the head group and the probe, they had about the same amount of quenching, which indicates that these lipids probably just bend back among themselves. They're not just in some perfect order that the length of the chain determines where they are in the lipid bilayer. And surprising to me was that the cholesterol labeled NBD was the deepest labeled in the bilayer, and it was virtually inaccessible to the quencher. So that's a reasonably positive result for a heterogeneous membrane. Another experiment that was done was to, now working with homogeneous lipid vesicles, was the quenching of fluorescent fatty acids, which are these shown over here, by a brominated fatty acid, using only one brominated fatty acid, which is here, and to see how the different fluorenyl derivatives were quenched by that brominated fatty acid. And as you can see, they're located, the fluorenyl group is located at a different number of carbon atom depths from the surface of the membrane. And when this was looked at with this brominated fatty acid as the quencher, it was found that this derivative with about 8 carbon residues was the most quenched with the concentration of dibromosteric acid. And as the carbon chain was made shorter, there was less and less quenching. So yes, this gives us some information about how these probes are distributed in the lipid bilayer. There are some more complicated methods than this where different brominated lipids are used to sort of triangulate where the fluorophore is in the membrane, but that's a little too complicated to explain. There's one important thing about doing any experiments when you're doing quenching in membranes, and that is the added quencher completely bound to the phospholipid? And that's not always the case. And the answer I have here, an example, is for doxyl stearic acid, which is partially soluble in water. And if you look at the quenching of an NBD derivative with the doxyl stearic acid, you find that it depends on the membrane concentration. That's what this alpha value is meant to be here. It's sort of the volume fraction occupied by the lipid vesicles. So the more concentrated the lipid vesicles, the higher the volume fraction of those lipid vesicles. So let's go to the highest volume fraction first, and we get a certain amount of quenching from the doxyl stearic acid. But if we dilute the lipid concentration, we see more and more quenching. And that's because there is a lower volume, the volume fraction in the sample becomes lower, and hence the concentration of the partial soluble quencher increases in the membrane. And so the answer depends on lipid concentration. That can be considered a negative thing if you were not paying attention to what your lipid concentration was, or alternatively could be a positive thing because the data can be used to determine the partition coefficient of the quencher between the water phase and the membrane phase. More detailed models for quenching of membrane-bound fluorophores are almost impossibly complex because there are too many factors that need to be considered. Let's just think of, let's say we wanted to build a mathematical model to describe the quenching and even the effects of diffusion on quenching. We have many different cases to consider. We would have to consider the case where the quencher can be in the aqueous phase or in the lipid phase. We would need to consider the case where both the fluorophore and the quencher are covalently bound to the lipid. That's another case. The covalent bounding of the quencher to the lipid can be at different locations. That's another case. Another case would be, are there boundary lipids around the fluorophore? The fluorophore might be located on a protein, which might result in more lipids of a certain type being concentrated around that protein or less concentrated. And many more models could be examined. So it's not very practical to consider, at least for me, for modeling this type of behavior in membranes, which would have to be something that would be done probably by molecular dynamics simulations rather than by any type of analytical calculation. So that is the end of part 8b. As I promised, it would be a little shorter than the previous lecture. And in the next lecture, we're going to deal with what I call unusual types of quenching behavior, because not all quenching behavior it looks like what we have here. There's other special cases where the quencher molecule can bind directly to the protein or bind within the protein. So we'll discuss some of those. I thank you for your attention, and we'll see you next time. Goodbye.